Hello, I hope you're well. We're going to get into the topic of integration now. Integration is a bit of a new topic. You may have seen bits and pieces of it. It is linked to primitive functions, but where we really start this topic is approximation methods. So one of the things we want to do is find the area under curves. So if you do have a curve, let's just draw something on here. So this might be, say, sales over time. And you might get some curve in there, something like that. And you want to find exactly how many sales have happened over each year. So what you can do, if you can find the area under the curve, that's actually the equivalent of telling you how many sales there were in total. I wrote 3 twice. So basically, well, if you've got 4 sales and let's say you sold sorry, trying to find my color palette. There it is. If you sold, let's say on average 6 items per year, then this area in here would basically be your sales, and your sales would be around 24 units. So depending on what the units are here, it might be thousands, it might just be products, but this area under here will be important in terms of finding how much something's happened over time. Sales is just one example of that. In terms of approximation methods, there are 2 we are going to consider, and they're both going to get us an approximation for the area under the curve. As you can see in my example here, my red area is not quite the same as the blue area. That's because the red's an approximation, so it gets the approximate area for us. So looking at our first method of approximating is called the trapezoidal rule. So the trapezoidal rule. And like you might expect, it does involve trapeziums. So for a trapezium, we should know the area formula. A equals, you might have seen it as h on 2, a plus b. Okay, so the height on 2, a plus b. So if you do draw a trapezium up, in case you've forgotten what a trapezium looks like, you've got a and b are the parallel sides, and h is the height down here. You may have heard the jingle. What is it? It says half the sum, so half the sum, the parallel sides, times the distance between them. So it's saying half the sum of the parallel sides times the distance between them. That's the way you find the area of a trapezium. And you can rearrange that, and that will find your area of a trapezium in general. What the trapezoidal rule is going to do, it's going to take some curve. So we'll have an equation. We'll have ourselves a nice little curve. Let's just start off here, and our curve will go like this. And we're going to find the area under that by assuming a trapezium shape. So the trapezium we're going to draw for our curve goes through here, the pink, up to here, and then it draws a straight line through here, and that is a trapezium. These are the parallel sides here. These, that there are parallel. So how large this is, I suppose, is a few labels. If we call this point here point A, this point here point B, this coordinate of this here will be A, f of A, if our curve, of course, is f of x. And this point here will be B, f of B. Okay. So there are 2 points. That means that this distance here, I suppose you're going from 0 to a height of f of A. This distance here is f of A. Similarly, this here is f of B. So the distance here is B minus A. We're going to leave it, just express it as just being h to make life a little bit easier. So my area under my curve, well, it's an approximation. I'm going to say that the area is approximately equal to, the funny equal signs there. Well, going back to my formula, it's h is the height. It's still the height because it's still perpendicular in here. H on 2. Then it's going to be the parallel sides. So parallel sides here are f of A and f of B. And that's the most general case of the trapezoidal rule. One worth remembering, if you can remember how it's derived, that's a good place to start as well. The formula sheet writes it slightly differently. So the formula sheet, just so you know, will write instead that the area is approximately equal to B minus A on 2 f of A plus f of B. This is the one they use. I generally don't like it. I like the idea of H better than B minus A because we deal with more than just one trapezium in most cases, most examples. Okay, so one trapezium, it does give us an okay approximation for area under the curve. Just color that in there for you. But what happens with this, the more trapeziums I draw in, if I draw another trapezium through here, if it was straight, that would give me a more accurate area under the curve because I would be going between here and here. That's slightly more accurate. Or if I drew another trapezium through here and here, I get a more accurate area again. Okay, and the more trapeziums I draw, the more accurate my area will be in the end. Obviously, a bit more calculation to do. Okay, so going to a more general case, that's just for one trapezium, and that's the one given to you on the formula sheet. So in general, you'll be asked to do more than one trapezium. So moving across, looking at something a bit more substantial. If I do have, again, another diagram here, we'll draw up a nice curve too. If I've got this business here, and I have my points A, got a point B here and a point C. My coordinates, my endpoints here are A, f of A. I've got here B, f of B. And I've got here C, f of C. Okay, so now doing it by doing two trapeziums. So my first trapezium will be this reddish side here. My second trapezium, I'll do this greenish side here. So first trapezium, that's kind of the trapezium I've got there. The green one, that will be my trapezium in there. In terms of heights, this is f of A, this is f of B, this is f of C, and I'm going to call h is just how big each one is. So that would be h in there, this would be h in here again, differently defined. So my first trapezium, getting right into it, my area under the curve is approximately equal to, well, the formula said h on 2, so it's h on 2 multiplied by the sum of the parallel sides, f of A plus f of B. And then for my green approximation, h on 2 again, the height, distance between them, it's h on 2, h is that distance there. And then it's going to be my parallel sides, f of B, f of C. We are always going to assume h is the same distance as well. So say h was 3 here, h would be 3 here as well. Those heights must be the same for the trapezoidal rule. Taking this a little bit further, what we can see is there's f of b that occurs in both of them. So I'm going to expand and then factorize, or I'm going to try and combine these. H on 2 appears in both of them, so I can say that A is approximately equal to H on 2. I'm going to have f of A from here. I'm going to have two f of b's, f of b there, f of b there. I'm going to have one f of c as well. Okay, so that will be these two combined, if you like. Generally, just writing it, notation, a is approximately equal to, and we say h on 2, f of a plus f of c plus twice f of b. Okay, so the first one, the last one, double the middle one. If we go a few more trapeziums, should really drive the point home. So looking at this one here, we'll start with 2 trapeziums, we'll go 4 trapeziums, and then we'll go 4 trapeziums here. So this will be A, B, C, D, and E. So this is f of A, f of B, f of C, f of D, and f of E. So my height being the same, height of each house if you like. So if you want, you can draw a little house on each one. H is the size of each house, little row houses, got a house in there. So height, how big each house is, the width of each house. Our area here is approximately equal to, my first trapezium here is h on 2, f of A plus f of B. My second trapezium is h on 2, it's going to be f of B plus f of C. My third trapezium, so this one here now, is going to be h on 2, f of C plus f of D. And my last trapezium is going to be h on 2, f of D plus f of E. Okay, so I've literally just done trapezoidal rule 4 times. First trapezium, second trapezium, third trapezium, fourth trapezium. Now this does generalize because you will see here f of B in here, f of B in there. You've got f of C there, f of C there, f of D here, and f of D here. And they are my middle ones. It's that one there, this one here, and this one here. So the middle ones all occur 3 times. So combining like we've just done, I can combine all of these here, and I can say h on 2, it's going to be f of A plus, and I'll include the f of E here because there's only one of those. There's one f of A, there's one f of E, they'll get together, plus there's 2 of everything else. So it's f of B plus f of C plus f of D. Okay, and so in summary, trapezoidal rule, h on 2, h is the height of each one, the first, the last, and then everything in between. Board of studies, formula sheets, textbooks, fudge this around quite a bit. I like to keep it simple, h on 2. So that's basically from the definition of trapezium's area, half the sum of the parallel sides. So back to our formula here, the very start, h on 2, a plus b. Then we include, so h on 2, the height divided by 2, the first one, the last one, and 2 times everything in between. It will be written a whole bunch of different ways. This is the method, this is the one I generally prefer. I would encourage you guys to write that down and write some description if you do need to. I'm going to head across to another video now and just do a few examples of this. You will find it's probably quite tedious, and I find it's quite tedious. If you get the rule down, pulling that out in exams is quite nice. Also, I mean, while I think of it, this is similar to the Border Studies formula on the formula sheet. That's the formula. That's the Border Studies formula right there. We're taking h on 2, first, last, and 2 times everything in between. Just summary of that. Worst case scenario in an exam, hopefully you can fall back on trapezium, 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 whatever number of times you do need to. Thanks for watching. Sorry it's a bit more lengthy. This rule is a bit lengthy, but yeah, it's not too bad once you've done a few examples, but the tedium can be a little bit killer.